Good morning, everybody. We're going to continue on from what we did yesterday and finish up chapter 7 as well. Remember, this whole section deals with inferences. Yesterday, we talked about estimating a population proportion. Today, we're going to talk about estimating a population mean. So basically, what we're going to have here is we're going to use the sample mean to estimate the population mean. So small to large. Similar to yesterday, we're going to use the point estimate what we talked about yesterday is that the sample mean is the best point estimate another name for that is a single value estimate of the population mean. Then we're going to look at confidence intervals. We're going to create those we're going to use confidence intervals to estimate mu. And in order to know this, we have to know the best sample size for our study. This finds the minimum number of subjects needed for your study to be valid. If you're looking at all the students at Dallas College, you can't just use 10 students in one class to estimate the 40,000 students we have. So if the number is too small, then it's not going to be valid, worth anything. All right, so first off, it's very rare. You almost never ever have the population mean, because to do anything with the population, it's very time consuming, very expensive, and there are so many biases that when student or whoever your subjects are provide false information or don't answer some questions or anything like that. So what we have to do is we're going to look at what really goes on is we take a small sample and estimate what happens to the population. The point estimate. What exactly is a point estimate? Basically, all it tells us here is, remember, we're using one point, one number, one value to estimate the population. So the point estimate, the number we choose, the number we use as a point estimate has to be the most logical choice. And that's why I said earlier that the sample average is the best, because it takes whatever we have for a sample and goes from there. So best point estimate. And confidence intervals. What is a confidence interval? How do we find it? How do we find it yesterday? What we ended up yesterday is we had, actually, there was proportions. So we had P minus our E to P and then P plus E. Where E is the margin of error. And yesterday we talked about proportions, so that's what we have there. Basically, it's what it's saying here that if our confidence level that's alpha, we could make it whatever we want to. We say it's 80%, 90%, 95%, or something like 99%. What that says is once we get our value, once we get our value for the confidence level, then we can calculate the margin of error, and then we can find our lower limit and our upper limit to what's going to be our mean in this case. So then, so we use a 90% confidence level, then there's a 90% chance that the population mean will be within these two values we calculate. So that's what the objective is for today's class. The symbols we're going to use. X bar we define, remember it's if it's a lowercase alphabetic letter, then it deals with the sample. Because there's a bar on top, it's the sample mean. The Greek letter mu, since it's a Greek letter, that deals with the population mean. That's X is your element selected. Then we'll talk about those later. Then we have S, the sample standard deviation. We have N, which is the total number of values or elements in our sample. And then E is our margin of error. As you read there, actually, you can see that in order for this to be valid, we have the same conditions we have yesterday. The required conditions they have to be continuous. Right, it has to be. Actually, there were four conditions made yesterday. They have to be exact. You have to be finite. They have to be finite number of elements, or with this case, trials. The must be independent. No, not today, no. No. All right. The sample must be random. And the last one is n has to be bigger than 30. Or normally distributed. What does normally distributed mean? Bell curve. The reason for that is because if it's a normally distributed, then 50% of both sides of the mean. And if we don't know that, then we have to have a uniquely large sample. So these are what we have to check at the beginning of each, because if one of these aren't satisfied, then we can't use this method. We have to use another method. The confidence interval. Last time we talked about our proportions, remember, it was P minus to P plus margin of error. But now since remember, we're trying to estimate the population mean. So all we know is a sample mean. So we have our sample, these are hats. So it's the sample mean minus the error is less than the population mean, which is less than the sample mean plus margin of error. And like yesterday, we could take different ways of representing these things. They could be in set notation. They could be these are all the same thing. Our margin of error. What is basically when we say margin of error, what are we talking about? It's in the name. What's a margin mean? It's a range. A margin. If we're is like in your papers, whenever you write a paper, you have the left and right margins. It's that's much we have wiggle room on both sides, 1 inch on a paper. So those are the margins of mistakes. So we have our 1 inch margin of error, which means if we needed more space, we could expand our text up to 1 inch. So that gives us a plus or minus an error. In this case, since we don't know the population, we are now going to use a different format. This remember when we did proportions yesterday, our error was the z-score, confidence interval divided by 2, and then PQ. It looks totally different because now we don't know the population. We're estimating it. That's what we use. This is called the t-score. which means it's a whole different table. And we'll talk about those in a second. And then we have the sample deviation over the square root of the sample size. So that's fine. Let's talk about the t-score for right now. The t-score. Used when n is large, or when the population mean is not known. So to use this, we know the alpha is the confidence level or level of confidence. But we also need a DF, which is the degree of freedom. And that's its own formula. The formula for degrees of freedom is n minus 1. With t-scores, we can have 3 possibilities. This is a one tail left, one tail right, or a two tail. And the table we're using now for this is use table A-3. It looks like this. Notice on the very top now, it separates for us whether we have a one tail or a two tail. And our confidence level is already calculated there for us. If it's a one tail test, there's the values. If it's a two tail, we have to do divided by 2. And so that's what we get here. It does it for us. So that defines our column headings, our confidence level. Our degrees of freedom, remember, is n minus 1. So notice ours goes up to 2,000 or even larger than 2,000. So it finds the same thing. It finds the area and those tails. We'll do an example in a minute, but we'll go through the rest of the words. The confidence level is our alpha. So if we say 95% confidence level, what does that correspond to? 0.95. So that makes our alpha what? Yeah, 5% or 0.05. How do we get this? We take 1 minus our confidence level equals alpha. So 1 minus 95% is, or 100, I should say, 100% minus 95% is 5%, or 1 minus 0.95 is 0.05. Ooh, that's not good. So to find alpha, one minus confidence level. There are endpoints where we define whether it's the tails, where the tails start, is our critical value or views. How do we find our critical values? Since our formula says it's the T alpha over 2, that's what we'll use. And remember, as yesterday, we'll always look on the right-hand side. Degrees of freedom. df equals n minus 1. What's the degrees of freedom used for? It's used to find fat. Because this is the left column numbers of table A3.
Professor, you just said that the degrees of freedom is used to find that. What exactly is that?
This value. Good question. It's this value. These are your T values.
Oh, to find the t-values?
Yeah. That's
Oh,
that
okay.
here. Yes. I'm sorry. Yeah. So if we were looking at an alpha of 0.05 and it's a two-tailed test. So let's look at this. Let's first just finish up this part here. So the rounding is 1 decimal more than what was used. In the data set. So it's like this. Alpha equals 0.05 and n equals 30. We want to know what is our alpha. It's a two-tailed experiment. And to determine if it's one or two-tailed tests, I'll do that after this. So what we have to do here is go to two-tail, alpha is 0.05, and what's our degrees of freedom? N minus 1. We go to this row and this column. So we go to 29, 0.05 is here for a two-tailed test. So it's in this column. We go all the way to 29, which is that one. Focus this there. 29 is that dark line right there, 0.05. So it's 2.045. So for our example here, our T alpha over 2 is 2.045 from the chart. Any questions so far? And the excellent thing about this sort of test is we can go, if we have, because our conditions are two, we have to have either normally distributed or it's got to be bigger than 30. In other words, if our data set, since this is less than 30, less than equal to 30, then we know for sure that our data is normally distributed. If we had 35, then it wouldn't matter. But anything 30 or less, we got to make sure we have a two-tailed test that's a normally distributed curve. So if we have anything less than 30, like we have 5 or 7 or 10, our sample size 5, 7, or 10, or anything like that, then we have to know for sure that it's normally distributed. Does it have to be exactly bell-shaped to be normally distributed? No. It's got to be roughly that shape. So normally distributed or n is greater than 30. That's to use the t-test. So if it's greater than 30, doesn't matter, we can use t-test. But if it's less than or equal to 30, then we have to make sure it's normally distributed, which means roughly normal. What does roughly normal mean? If we were looking at a bar chart, is that normally distributed? Is it roughly normally distributed? Yeah, because it goes up, it reaches a maximum, and it goes back down. So that's what we mean by roughly normal. It has that basic shape. And look at our data set. How do we know this is roughly? Because only has one mode. Which one's the mode? The mode by definition is the most frequently occurring. So it's the tallest one. We only have one tall one. And more importantly, no outliers. The reason for the no outliers requirement is because outliers drastically change our calculations. The confidence level. It is important because it allows us to define our confidence interval.
Excuse me, Professor. Is
Yes.
confidence level the same as confidence interval?
No. No. This is an interval. This is a level, a single number. And this is what I was going to talk to you about in a second. The confidence level is your alpha. The confidence interval is, in this case, that's your confidence level. So this degree of confidence, because it's always some percent, let's say 90%, this changes the value for our margin of error. And since it changes the values of the margin of error, it changes the width, the range of our interval. The range is the distance between a smaller number and the largest number. So as this number changes, for example, this interval could be wide there and it's getting more narrow. Because the more confident we are, then that means we are very almost 100% sure we know what the population mean is. So what's happening there is our intervals get smaller. And that's why always, when you do a research project, always start with the highest. And if your population, if it sounds reasonable to be at a higher one, then great, keep it there. But if not, then you go down to the next lower one, go down to the next lower one, till it gets to a value that it works. And I'm looking for some of the examples here. We haven't gotten to there yet. The student T distribution, or just the T distribution, it has this formula. Because remember, in the whole purpose we have in this section is we're estimating the population mean from the sample mean. So our numerator will take those into account. This kind of looks like the beginning of the standard deviation, x bar minus, or x minus x bar. This is the smaller one, this is the more accurate one. Over our ratio of our standard deviation. So whenever you have to find the T distribution, this is the formula, mechanically, how we're going to get the values. Or we can always use technology or the tables once we know the information. Again, degrees of freedom is n minus 1. Oh. How to calculate alpha, or the T alpha over 2, the critical value. Again, there are two ways we can do it. We can, fastest way is by using the software, either StatDisk, the Texas Instrument, the calculator, Excel, or programming language. You could program anyone you want to in those. So if not, then we can also do it mathematically. And I'm looking for an example for this one. Oh, in your table, in your example, depending on your sample size, it changes your distribution. So the top one, the highest one, is your standard normal distribution. That's the general set we use from calculations. Now, depending on how many values we have for n, the larger we get, the closer we get to the actual calculation. The smaller we get, the less accurate we become. So again, the whole concept of statistics is the closer you get to the population, the closer your actual answers become to being real. Let's go to example 1. Find the critical value. So the question says, find the critical value T alpha over 2 corresponding to 95% confidence level. Given n equals 6. So what does that tell us? Before we do any calculations, what does that tell us? What do we know about the shape of this graph? Right. It's normally distributed because remember, n is less than 30. Since it's less than 30, it's got to be normally distributed. So we know the graph is going to be a bell shape, or we're going to make it our shape. So what do we do first? We know n. What do we have to find first? We use n to find our degree of freedom, which was n minus 1. So 6 minus 1 equals 5. That's the first thing we know. The second step, find alpha. How do we find alpha? Alpha equals 1 minus your confidence level. So it's 1 minus 0.95, which is alpha is 0.05. Doesn't tell us anything else in there. Find a critical value of that corresponding there. It doesn't tell us anything else. So do we use a one-tail or a two-tail test? It says it doesn't specify. Then we're going to approach this as a two-tail test, which is always the drawback. I mean, the fallback to. The reason being, because if we use only a one-tail test and we use the wrong side, then we're 100% wrong. But if we use a one-tail test, then when we use a two-tailed test, then we'll get the answer. We may have too big of a number, but we'll at least have the correct answer in there somewhere. So since it is a two-tailed test, we divide alpha by 2. Because alpha is the total area of both these places put together. Let's call this one alpha 1, this is alpha 2. So alpha is 0.05 divided by 2, we get 0.025. All right, so we found in this case, our alpha. Our alpha over 2 is 0.025. And it's a two-tailed test. So step 3, find what we're looking for, the critical value. Value or values. How do we find the critical value? Our table. We know we have a two-tailed test. Our confidence level is 0.025. All right, we use 0.5. Man, I can't barely read these. Since our initial alpha was 0.05 and degrees of freedom is 5. 0.05. Go down to 5. We got 2.571. So our critical value T alpha over 2 is 2.571. Again, so why didn't we use this? Well, because this tells us the area of both, the size of each tail. We don't know exactly where it's going to fall because it's a two-tailed test. All we do know is in our case, alpha is 0.05. That's what we use. And that's why it distinguishes whether it's a one-tail or a two-tail test. If that doesn't make sense. Okay. Overall, the alpha is 0.05. That's if we use the one-tail test. Since we're using a two-tail test, if each of our tails is 0.025. So to use our chart, if we use the 0.025, then it's a one-tail test. If we do one-tail test at 0.025, which is half of our 0.5, then we go to the same thing with the same value. So that's why it's much easier just to go to the alpha as one tail. All right, another example, example 2. It says confidence interval using peanut butter cups. Listed below are weights of randomly selected Reese's peanut butter cups miniatures. They're from a package of 38 cups, and the package label states that a total weight is 12 ounces or 340.2 grams. If the 38 cups have a total weight of 342 grams, then the cups should have a mean weight of 340.2 divided by 38, or 8.953 grams per cup. So that's saying that's the average weight of each cup. Use the listed sample data to find the point estimate of the mean weight of the peanut butter cup. Use the listed sample data to construct a 95% confidence interval estimating the mean weight of that. So let me write down the information we have here. So we have there, N is 38. The mean weight of our sample is 340.2 over 38, which is 8.953 grams per cup. Okay, so 1. Find the point estimate of the mean weight of the candy. That's an easy one. That one is super easy. Then the second one is construct a 95% confidence interval estimate of the mean weight. And our data was 8.639. Here's more data. The point estimate. Remember, the first thing we talked about when we defined point estimate, we said that the best point estimate is the sample mean. So for this one, that is your point estimate. It's the sample mean. Now, the second one says construct a confidence interval. Remember our conditions that we have to have. What are the conditions? They have to be independent. Each event. So in other words, when you take one candy, does that gonna affect the weight of the next candy? No, it's independent. So each candy has its own weight. Are they random? Yeah, you open the bag, you take one, you don't know what's inside the package. It's just, it's just candy. So it's random. Is it normally distributed? Or does it matter? Doesn't matter because our sample size is bigger than 30. Since it's bigger than 30, we can go ahead and use the t-test. Or the t-distribution. So what's our formula for this? What do we need? What do we need? How do we just find it? This is the value from the table. What's our alpha? Because it's a 95% confidence interval. So 1 minus 0.95 is that. What's our degree of freedom? Where's my data? I'm missing the sheet I just wrote. Confidence t-test. What did I do? Wait a minute, let me put it back on there.
Wouldn't the freedom be 5?
Why would it be 5?
Because isn't n was 6?
Why would it be
My-
6?
I thought that the given information was that we knew that n was 6, and you do 6 minus 1, and that would give us 5 to find the degrees of freedom.
No.
Okay.
First off, let me ask you, are you looking at the sheets that I sent out?
No.
Yeah, you had to because I didn't give you any data. How'd you get 6?
I was remembering from when you started working the problem. That probably was a different problem though.
No. No, I'm looking for
Professor, can we say
Oh,
12
yeah,
minus
yeah.
1?
right here. These are my data points. 1, 2, 3, 4, 5. We only have 5 data points. So our N of our sample is 5.
Okay.
So our degree of freedom
Would be 4.
is going to be 4. Yeah, that's why I ask you guys, don't you just read off those sheets I give you. Yes, the sheet itself was, but I like to change, I'm gonna start changing those to up now. So I'm gonna give you these 5 pieces of data of our sample. Now from there, we calculate our own t-values. Is it a 1-tail or a 2-tail test?
Should be 2-tail test because it's less than 30.
No, the size doesn't matter. Because remember, we're trying to estimate the population size, average. So think of this. Can the candies be always greater than that population average? Or always less than? Or when we pick a piece of candy, it's going to be on either side? It's 2-tailed because when we pick a piece of candy or a Reese's peanut butter cup, the weight of that candy can be either less than the population average mean, or it could be greater than it. So because of that, we have a two-tailed test. If if we're looking for values that are always greater than it, then we have a one-tail right. If we're looking for all the values that can be less than, then it's a one-tail left. But since all we're doing is taking candy from a bag, that weight of that candy can either be higher than the average, population average, or it could be less than. So it's a two-tailed test. So we're using a two-tailed test. So what do we have then? We have a two-tailed test, alpha is 0.05. Our degrees of freedom is 4. So we're using 2.776. So that's our t-score value. Now, what else did it give us? So I'm missing some information here. It tells us $38 cup. We're only using 6. There's 38 in each bag. We only use 6. I'm missing a value because remember, in order to find this range, we have to find X minus the error, X bar plus the error. That's the interval we're looking at. And the formula for the error is our t value, which we just found here, is 2.776. Times our standard deviation divided by our sample size, square root of it. We don't have the standard deviation. We can find the standard deviation of these numbers. How? How do you find the standard deviation of a set of data? Remember the formula? X minus X bar over N. So for this set of data, we have to create a table. Let me go ahead and go to it is 5. And it's 5. Oh. Catch. So I'm going to go through here now. I'm going to find the standard deviation. So these are my X's. So I have 8.639, 8.689, 0.548, 8.9336, 9.042.
43.854.
You didn't put a decimal on one of the numbers.
Oh, yeah, you're right, you catch. That would really ruin it. Now, we're standard deviation. Where's standard deviation? There's standard deviation. Standard deviation of our data. So our standard deviation is 0.208892.
Professor, please, how did you get that?
Have you ever used Excel before? Have you ever used Excel?
I can't remember again.
I mean, I'll take it as a no then. It's a tool that Microsoft has. Since I'm looking for a standard deviation, I remember Excel is a referential database. So I always start my calculations with an equal sign. I have to give the command what I wanted to do. So it's going to be a
Yeah.
standard deviation. So I start with ST. I look down here on the options that I have so far, and I have standard deviation, deviation. These I can't use because those are from the old ones. So I use standard deviation A. Now, this one gives me how I would calculate it. So this one estimates standard deviation. I need to know from what data set, my beginning value, second value. So I highlight those. And then hit equals. So I type in the equal sign STDEVA, open parenthesis, and then I highlight these, and then I close parenthesis, hit equals. So to find my t value, I have to use my t-test, to find the error. T value was 2.776. N was 5. And S is that value. So to find my error, I take my t value times the standard deviation divided by SQRT, the square root, open parenthesis, of my n. Oop. I missed that one. That one should be 10. So that's my error value. .259332. Again, so this formula, I have my error. I take my t value. If I double click this, I'll show you. I take my t value, multiply it, and I put this parentheses because now it's the s over square root of n. My S was this value. That's at location H10 divided by SQRT, the square root, open parenthesis, the square root of N, which I clicked that. That's at 9 H9. And I hit enter. And that gives you my error. So what I gotta do now is to find my interval, I gotta do my X value minus my E, X value plus my E. My X value was 8.953 grams. So it's 8.953 minus my error, 0.259332. And just same thing on this side. So I have 8.953 plus 0.259332. So I have 8.953 minus my error, which gives me that one. And then the other side is 8.953 plus my error. Oop. Plus my error. So this is my confidence interval. But what's wrong with the numbers? Why are these wrong? What does the rounding rule say? It's always one more than what the original data was. Since that's 3 decimal places, we
We
need
have
4
to
decimal
round it,
places.
we have to round it to 3 decimal places too,
4 decimal places.
4 decimal.
Because the data is 3 decimal places, we have to go one more higher. So we have to round it to 4 decimal places. So that's my answer.
And standard deviation, are we not supposed to round that one too? And the error?
No, only ones you want to round is the final answer.
Okay,
Yeah, because if you round these two, then what you'll end up with is something called a round off error, which may change it enough. And so instead of 9.21, they'll make it 9.323 or something like that. So it'll change it just enough so it's no longer right.
okay.
Let's see any more examples. Well, examples. So if our sample is neither normally distributed or n is not greater than 30, then we can't use that method. So we can use here we can use another method that it's called resamples the data. This is in quotes. For an example, we can use a bootstrap resampling for computing the confidence interval. So what this does, it takes, reason it's called resampling, because it takes us and allows us to repeat the sampling process numerous, or repeat the process multiple times. So we can resample the sample data multiple times. As we saw in our list, we have up to 2,000, if not more, n values we can use, degrees of freedom. So for this, you can't really do this. You can't do this manually. You have to use some sort of technology. And actually, the easier one that I've seen that to play with is the stat disk, because all you have to do there is enter the data in one column and then just have it run, just point and click from there on out. So that's what I'll do on Thursday. I'll go through all these examples, a bunch of these examples, and show you how to use stat disk to see what our values are going to be. Because I want to make sure we get that far at least. Here's an example. Critical thinking. Sales of vinyl records, which are called LPs for long playing. The example says this: the sales numbers are listed below. I'll show them in a second. In order by year, beginning with 1993. Use the list of sample data to construct a use data to construct a 95% confidence interval of the population mean. Is the confidence interval method described in this section a good tool? And the third one, apart from the confidence interval, is there some other tool that would be better for gaining insight into the nature of the sample data? What is the most notable difference about the sales numbers? Any other tool we can use? And the data. The data is, here's the question, here's the data. These are all the data by year, starting from 1993, 93, 94, 95, 96, 97, so on and so forth. If we count them, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, we have 26. So let's see what happened here. Now, using the listed data below, is this a one-tail or a two-tail test? Any guesses?
%, confidence interval. I think it should be two-tail test.
Well, no, actually, this information we have here so far, because we have our n equals 26. We went 95%. See, yeah, we can't tell from this. We know this n is 30, less than 30.
Less than 30, yeah.
So it's got to be a normally distributed. We're assuming that it's a normally distributed curve.
Mhm.
So now it's the question is it a one tail or two tail? What is this telling? What is this telling? What's the data saying? It's the sales numbers are listed in order by year. So what they're looking for here is, can the next sale, is it always going to be above, always going to be below, or can it be higher or lower than the current population mean?
It should be higher
Why higher?
because already we use data 95% so confidence interval. Then it will start adding up.
How do you mean?
You know, when we draw a two-tail test, when we draw the normally distributed curve, that's the bell curve, the 95%, we take, it's going to be 1 minus 95%, so we get 5% for distributing to the two tails. That would be 0.25, 0.25 on each of the tail. Then our alpha I don't know how to put it, sir, but I know it should be two-tailed.
You're right. It is gonna be a two-tailed test. For the logic you put, is because it could be higher or lower. It's not always gonna be higher.
Mhm.
So with a 95% confidence interval and our N, that for our data set here, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, our degrees of freedom is 25.
That's 26 minus 1.
Right. So it's 25 at 95% confidence interval. So two tail at 0.5 at 25 gives us 2.060. Gives us 2.760 or 2.060. So it's going to be your confidence interval to be 2.060. Or actually, it's going to be 2.06. We have to find our mean, by the way. Because remember, what we're looking for is this. So we have to find the sample mean. So we have to find the mean of all our data. And then we have to calculate E. T alpha over 2, standard deviation over square root of n. All right, let's get to it. So our data is 0.3, 0.6, 0.8, 1.1, 1.1, 0.4, 1.4, 1.5, 1.2, 1.3. So let me see here. Yeah, we have 26 numbers. That's what we needed. So X bar equals so this is our X. Now it's going to be X minus X bar. So it's that number minus that number. Since since I want that to be stationary, I put dollar signs in front of it. So that's my mean. Okay. Remember I said if you add up all these, the X minus X bars, what should they equal? This should equal 0. What this number says here, it's 1.42 times 10 to the negative. So move the decimal place 14 to the left. So it should be 0.0000000000001421. So this is pretty close to 0. So now we got to do X minus X bar squared to the power 2. So it's like this number times itself. I get that. And now to find our standard deviation, I take the square root of that number divided by n, which was 26. So that's our S. All right, so our interval will be our t value, which was 2.06 times now this is our error, times that divided by SQRT of 26. So that's our error. So we have our mean is this one minus this one. And then we have our mean plus our error. Since our data only had one decimal place, then we go to 2 decimal places. Oops. So there is our confidence interval. That's our CI. So if I entered all the numbers correctly, yeah, this is what it should be. This is the 20, all those divided by 26. Add a x minus x bar, square them. Then, okay, let me show you what I just did there. Okay, what I did, because we have to use this formula. And we know the formula for x bar is the summation of all our data divided by n. And E is the t value times s over square root of n. So in my Excel spreadsheet, on the first column, I had my x's. I added up all of my x's. Then to find the mean, I took my summation of all my x's and divided by n. That's what I found my mean. So that goes there and there. Then I took x minus x bar. So each one of these minus my x bar. And I first added them together, and it should equal 0. Because they have positive and negative numbers. To get rid of the negative numbers, I squared each one of those. X minus x bar squared. I first find the variance, which is the summation of x minus x bar squared divided by n. And then to the standard deviation is s. It's the square root of s squared. So it's the square root of the summation of x minus x bar squared over n. That gave me s. I needed s to find my error. So this value goes on top. My n was 6. This was from the table at alpha equals 0.05 and n equals 26. So the degrees of freedom is n minus 1, which is 25. And I put it all together. And that gives us, I will find this value, then multiply that, divided by square root of there. We have our E. And then I subtract my mean from it, and I add my mean to it. And that gives us our interval. Is it a good tool? Is the interval a good interval? Not really. Because our sample size was less than 30. So we're approximating it with a very small sample size. And there could be other ones depending on how the data is collected. But yeah, and we'll show how to use the software, the stat disk, once I have it downloaded on my computer. Finding a point estimate and the margin of error from a confidence interval. Remember, a confidence interval is X bar minus E, X bar plus E. This part here, this is the lower limit. And this is the upper limit. Upper confidence limit is upper C limit. But we just call it upper and lower limit because they're at both ends. To find the point estimate, to calculate it, the formula is, so the point estimate of mu is our X bar becomes the lower or the upper limit value plus the lower limit value divided by 2. Remember, we said that the sample mean is the best approximation of a point estimate of the population. And then the margin of error which is E, the same formula except a minus. Upper limit minus the lower limit
No,
divided by 2. So only thing difference are the signs between there. So here's a small example. If the confidence interval is 1030, what are the point estimate and the margin of error? That's a comma. So what this tells us, remember, the confidence interval can be written like this. 10 is less than mu is less than 30. It can be written as an interval, or it could be written as plus or minus E. X bar mass. So it's plus or minus 10 from the mean. So this is our lower limit. This is our upper limit. So the point estimate of our mean
Upper limit
is
plus
30 plus 10
divided by
over
2
2.
plus 20.
And the margin of error
30 minus 10 divided by 2 plus 10.
Right. All right, let's look at the next example. Second hand smoke. What this example is going to allow us to do is we're going to use the confidence interval to compare data. We're going to compare data, the samples, the intervals, and everything else between two different sets. So we have to use here this table. Let me draw this table here. We have negative 25, 0, 25, 50, 75, 100, 125, 150, 175.
200, 225.
I ran out of room. Oops, should have started. All right, what this one says, we have one group of data that goes from 0 to 50. This is people
Not exposed to smoke.
not exposed to smoke. Then we have another one from 25 to
So
roughly about 115.
115, yeah. People exposed to smoke.
Exposed to smoke.
And then smokers.
And then from 150 to
50
220.
to 1 to 220. 220.
5 or 220. Yeah, about 220. That's perfect. And these are my smokers. So what does this thing tell us? It says this graph shows confidence intervals estimates of the mean cotinine level of each of these three samples. People who smoke, people who don't smoke are exposed to tobacco, or people who don't smoke and are not exposed to tobacco. Now, because cotinine is produced in the body, when nicotine is absorbed, this chemical is a good indicator of nicotine in smoke. So it combines with nicotine. So that's how they can test to see the level of exposure you have. This chart, we see that the confidence interval of the smokers does not overlap. Smokers and these guys don't overlap. That's a good idea. So if these people who are exposed to smoke. These are not exposed to smoke. And this is their level of continine. And these are so there's no exposure to all this 100% into smoking. They have a high level, and this one has low level. So we can tell that smoking, these people don't smoke. However, these do overlap by this much. But again, that's so small and we don't know these are not exposed to smoke. These are exposed to smoke. So only thing we could summarize with looking at this is that people who have a low exposure have a possible overlap with people who have no exposure. So that should just be natural in the human body. Some people have it high elevated. These people could be there. It's just that they're in the wrong place, wrong time.
Mm. Like somebody staying close to a smoker. So it can be that such person is exposed to some percentages of the smoke.
Well, yeah, even if no, that's a good point. Even with the person not smoking, they have it on their skin, on their hair, on their clothes.
Mm.
As you said, just by standing next to them, you could assimilate some of that chemical.
Mm-hmm.
And you could definitely tell when somebody smokes because they have that unique odor. So that's if they have nothing in common. So this is, notice we're comparing 3 different studies here. And we'll see where their confidence intervals overlap. And then we can make assumptions from there. Estimating mu when the standard deviation is known. So now, if we know the population standard deviation, now these are going to be a lot easier to calculate. So our error is going to be the same. We're using a z-test here. But since we have the population mean, simply we have to use that. We use the t-test when we don't know anything about the population. Since we know this, it tells us we have to use the z-test. Okay, and the same condition, it's got to be random sample n is greater than 30. Let's see. Oh, this is important. Choosing the right distribution. The condition, if the population deviation is not known and it's normally distributed, or the standard deviation is not known and n is bigger than 30, so again, it's one of these two, then we use a t-test and the sample deviation. If we know the population deviation and it's either normally distributed or n is bigger than 30, then we use a z-score and the population deviation. But if it's not normally distributed and it's less than 30, then we have to use another non-parametric method. So if you know, basically, both of these have overlapping of normally distributed and the n is over 30. Those are one of those two conditions. If it's not, if the population is not known, then we have to use a sample deviation, NT. If we know the population, we use the population deviation and we use a Z. So if known and normally distributed or n is bigger than 30. We use the Z-score. Estimating sample size. The symbols we'll use the mu. Remember, it's the Greek letter, so it's population. Population, and that represents the population mean. The rho, this little loopy thingy one, since it's Greek, it deals with population. And this is standard deviation. X bar is our, this is our alphabet letter, it's a sample. E is the margin of error. And Z is our Z-score for our confidence interval. So as it says here, it's the area of alpha over 2 in the right tail of the normally distributed curve. So notice here, we have population information. So because of that, we're going to use a Z. And we're using the right-hand rule. The right-hand side. So the sample size formula. We start off with the E. What we want to do is we're solving for N. So first thing, get rid of any fractions. Since this is rho over the square root of N, we multiply the square root of N to both sides. So these cancel. So E square root of N equals Z alpha over 2 times rho. Second step. divide by E. We're trying to get N by itself. So we divide both sides by E. Now to get rid of the square root, square both sides. So that cancels. We have N. And on this side, we have Z our times rho over E, all that squared. So that tells us our sample size. Note, because we're dealing with a sample size, round up, always round up. The reason being, because if you're studying human subjects, then how can you have a 0.3 or 0.1 of a person? So, and it's better to have too much than not enough. Let's look at example 5. IQ scores of stats students. Assume, here's a question. Assume that we want to estimate the mean, okay. Estimate the mean IQ score for the population of stat students. So the question is asking, how many statistics students must be randomly selected for IQ tests? How many students do we need if we want 95% confidence that our sample mean is within 3 IQ points? Of the population. Estimate the mean IQ score of the students. That's what we're looking at here. How many students do we need if we want to be 95% confidence that our sample mean is within 3 IQ points from the population mean? So what this is really saying is this. Here's the population mean. We want our scores to be within 3 points. These are threes. So we're taking our score and subtracting 3, our score and adding 3. Remember, this is the same as x minus e, x bar plus e. So we know that e is equal to 3. So what are we going to figure out? Now we have to figure out what is n. Alpha over 2 times rho over e squared. Oh, crap. I left something out. Because we can figure this out since we know the alpha. We know this, that's our E, this value here. I missed this part. When you determine the required sample size, not constructing confidence interval, here are some ways to work around not having the value of rho. Range rule of thumb. Using the range rule of thumb to estimate the standard deviation as follows. The rho is equal to whatever the range of your data is, the high minus the low, divided by 4. With a sample of 87 or more values randomly selected from a normally distributed population, range divided by 4 will yield a value that is greater than or equal to rho at least 95% of the times. So that's one way. It's the range divided by 4. That's n. Rho, I mean. Start and improve. Start the sample collection process without knowing and using the first several values. Calculate the sample standard deviation, S, and use it in place of rho. The estimate value, I forgot these, of rho can be improved as more specific or sample data are obtained. So that was an iterative process because you start with an initial guess or a calculation, and then you keep on adding more to it. Prior results. Estimate the value of rho by using the results from the other earlier studies. In addition, we can sometimes be creative in our use of other known results. For example, Webster IQ tests. So this is what's prior results. So this is already known. IQ tests are designated so that the standard deviation is 15. So we don't have to calculate it. It's given to us. Statistics students have IQ scores with a standard deviation less than 15 because they are a more homogeneous group than people randomly selected in the general population. We do not know the specific value of rho for statistics students, but we can be safe by using rho equals 15. Using a value of rho that is larger than the true value will make the sample size larger than necessary, which the bigger the better. But using a value that's too small will give you a very inadequate because we're going to underestimate it. So when determining the sample size n, any error should always err to the size that's larger. Always go too big and too small. So for our example, our row is 15. So our Z value with our alpha is 0.05. Again, at 95% confidence interval. We know our Z value for that is 1.96. We did that yesterday. So let's figure out what our sample size has to be. So our Z value is 1.96 times 15, and our E is 3. 3 goes into 15 5 times. 5 times 6 is 30. 45 plus 3 is 48. So it's 9.8 squared. Which 96.04. So we have to round that up to 97 people. So our N is equal to 97. Yeah, it's much easier, much faster. And I will try to put something together so we start using the stat disk to make life much easier for you. Because even Excel is very cumbersome. I will load it on my computer, my laptop, and bring it tomorrow. And I'll show you how to use it. We should get a free access code to it through our publisher. So I'll get the code and everything. All right. That's it for chapter 7.